Make your RTBH better with this one weird trick. Welcome back to the Service Provider Technology series. This video covers another topic from the domain of BGP security, source-based remotely triggered black hole filtering, or SRTBH. Before we begin, a few words on continuity. This video happens to be part of a longer series on BGP security which can be found on the channel. If this is your first time covering RTBH, you are highly encouraged to watch at least the first video in the series, if not the first two videos. The first video covers this topic conceptually, while the second video is a live demo of destination-based RTBH, and in fact the demo later in this video builds on that demo directly. But as for this video, we will introduce the concept of source-based RTBH and what differentiates it from the original form of RTBH. We will talk about the underlying concepts that are utilized to facilitate this type of implementation. Finally, we wrap up the topic with a live demo of SRTBH. Let's begin. Source-based RTBH builds upon the infrastructure laid down by destination-based RTBH to provide more granularity. Recall that in destination-based RTBH, the victim of the DOS attack was essentially taken offline. What happens after that depends on the security planning, but hopefully at some point the attacker can be identified and the traffic from it filtered. Source-based RTBH can be one of those options considered to implement this. We will cover exactly how shortly. Since the core concepts are the same as destination-based RTBH, BGP is still essential to signal this information in the control plane. So the question becomes, who will originate the BGP NLRI? With destination-based RTBH, we had options. With source-based RTBH, if it needs to be done responsibly, the customer BGP device should no longer be a signaling device. Here is the issue. The attacking IP address would not, well, hopefully in a perfect world, would not belong to the customer IP space. So would an SP actually allow a customer to originate routes that it does not own? Thus, the SP now needs to stand up a dedicated trigger router to perform RTBH route origination. When it comes to the trigger router, though, it still has those multiple options that it had in the destination-based scenario. It can use communities to signal the intent to black hole traffic, and alternatively, it can alter the next hop attribute to achieve the same result. Time now to look at what makes this implementation actually work. As the previous slide already hinted at, all the concepts discussed in destination-based RTBH also apply here. So, RTBH will leverage the BGP discard route, albeit in a different manner than destination-based RTBH utilized it. And it has the option of using BGP communities just like destination-based RTBH. Psst! If this is the first time you've heard of these terms, guess where these concepts are fleshed out? That's right, the first two videos of this series. Now, for the special sauce, the glue that brings everything together, Krasinski's gem to Rain's Dwight, the Garfunkel and Simon and Garfunkel. Okay, forget that last one, okay? We are, of course, talking about uRPF, or the Unicast Reverse Path Forwarding Check. Well, all that is well and good, but what is this uRPF? Unicast Reverse Path Forwarding Check is a general security feature that is unrelated conceptually to RTBH and can be used in non-RTBH setups just as easily. The best short description of this feature, in my opinion, is in RFC 3704, and I quote, "Strict reverse path forwarding, strict RPF, is a simple way to implement an ingress filter. It is conceptually identical to using access lists for ingress filtering, with the exception that the access list now is dynamic." Well, for those familiar with multicast and its concept of RPF checks, this is exactly the same thing, except now we subject even unicast packets to this check. And time for a shameless plug. By the way, if you want a concise description of that concept, watch the first few minutes of Lecture 2 IP Multicast Routers and Routing Protocols video from our CCIE JNCIE IP Multicast lecture series. One small luxury of running your own channel are the shameless plugs. Very concisely though, the router will now perform an additional check on the ingress packets coming into it. This check is performed on the source IP address carried in that packet. So the router looks up a route for this IP address, the source IP address that is, in its forwarding table, something it normally does only for the destination IP address. The idea is that if there is no asymmetric routing involved, the ingress interface of the packet must be the same as the egress interface of the route that the fib has installed. If that does not gel immediately, just listen to the last 20 seconds carefully again till it does. But what I have described just now is actually termed strict uRPF check. With this method, if the ingress interface of the packet and the egress interface of the route do not match, there's not a one-to-one correlation, the RPF check is considered to have failed, and the packet would of course be dropped. This can of course cause some problems, especially in multi-homing scenarios with asymmetric routing, so there is a more lenient version of this also defined. This is the loose mode uRPF check. The only condition for successful loose mode RPF check is that the route must be present in the fib for the source IP. Where it points to does not matter as long as a route exists. So you do a lookup on this source IP and you are able to find a route. The RPF check is considered to have passed. And yes, a default route can be used for loose mode uRPF to essentially verify the entire IPv4 or IPv6 space, and sometimes that does defeat the purpose of uRPF based on your particular scenario, but that is not our concern today. I am not touching that topic. Our concern is how loose mode uRPF check treats a source IP lookup that results in a discard route in the fib. Now, if you've been following so far, you should say, but the loose mode is unconcerned with the egress interface. Only the route must exist. You just said this. Technically, you would be right. Except depending on the implementation, an exception can exist only for a discard route specifically. So any packet whose uRPF check pulls up a discard route can be considered a failed check. Even though the route exists, if it's a discard route, it can be considered as a failed check, and based on that, the packet can be dropped. In fact, for SRTBH to work properly, an implementation must have this exception baked in. It will not work without this exception. So to summarize, if the uRPF check in loose mode with the discard route exception is implemented, then any ingress packet with a source IP address that points to a discard route in the fib can be easily dropped. Well, how does this tie into SRTBH? Very simply, actually. The trigger router will now originate a specific route, but not for the destination like it did in the previous scenario. It will originate that route for the source IP, that is the attacker's IP. With everything else being exactly the same as RTBH, the edge routers should install a discard route for this IP address. And finally, if the uRPF check is enabled on the border interfaces with the discard route exception that we talked about, then this discard route will be used by uRPF check to drop all the malicious traffic coming from that attacker. See? Simple. Time to see SRTBH in action. And this is the same setup as we had for destination-based RTBH. Quickly going over it, there is a victim that is found right here. And there are two addresses out on the internet that we are tracking. There is a good guy address, and then there is a bad guy address. What's going to happen then is we somehow have to know the bad guy source IP, and then the good guy source IP is something that we just do not track, but we'll use this in our example to see which traffic is not going to be affected. Once this bad guy source IP or bad guy source network is known, the RTBH router will then introduce a route for this bad guy source IP address, maybe /32, maybe /128, whatever is the setup, whatever was determined. That particular NLRI will be introduced in BGP. It may be tagged with that next hop, that is a discard route, a well-known address for IPv4, a well-known address for IPv6. It may be tagged with that community, maybe the 666 community or whatever is the RTBH community. It would probably have those other things set up, such as the iBGP origin, the local preference elevated to 200. All of those things are the same. The only thing that is different is which route is being introduced, and that happens to be the bad guy source IP address. Once this NLRI is originated, it'll of course be advertised to all of the ASBRs, the ingress routers. Those ingress routers will take this bad guy source IP and they will start pointing it to a null zero or a discard route. So essentially they are black holing that traffic as a destination. But the difference here is we also have the uRPF check happening everywhere, and this is what is going to make the difference. So suppose the traffic comes in from the bad guy and it hits one of the routers. The next thing the router is going to do is do a uRPF check, which essentially looks up that route in the fib. And in the fib, it'll find that pointed to a null zero interface, and this is where that exception to loose uRPF is very, very important. If in loose uRPF, the discard route exception has been baked in, that traffic is now subjected to a drop because this is the source IP. It is pointed to a null zero route. That means it really does not pass the uRPF check and it is dropped at all of the edges. So we have now been able to more granularly drop the bad traffic, whereas the good traffic, because we are not doing anything to it, it should pass the uRPF checks easily, and it should be able to enter the network and finally get to the victim, which is hopefully not a victim anymore. So this is the major difference, the uRPF check and the discard route that has been originated by the RTBH router. Those two things are different. Rest everything is the same as destination-based RTBH. Time now to wrap this topic up with a demo. Now for this demo, we are using the same topology that we use for destination-based RTBH. The scenarios for the most part are the same, except the customer is not going to be involved in the signaling process anymore. So we basically somehow figure out who the attacker is, and then we use source-based RTBH internally to block that attacker. There is also a difference in the next hop attribute-based RTBH, especially when it comes to IPv6, but we'll talk about it once we come to that topic. So let's quickly take a look at what we have here. So we still have the same victim. That is going to be CE8. So CE8 is still our victim, and the bad guy is still in AS201. And the good guy is still in AS200. Now, on the INET side, we have to make some changes, but before that, let's talk about the uRPF. So that would be the first thing to set up on all of these routers, and we're going to set up uRPF on the ASBR, so the XR, the iOS router, and the SRX router as well, but that one comes with an asterisk. And the reason for that is the SRX that I'm running, the actual code, does not support that discard route exception. So it does support uRPF, but it does not take into consideration the discard route, which is essential for the functioning of source-based RTBH. So it can be done on some of the MX platforms, according to the documentation, some of the T series platforms, but as far as I know, not on SRX, but definitely not on the version of SRX that I'm running here. So we would be taking this out. And since we're also running ICMP, we also, when we are demonstrating, we would also try to pin the traffic using BGP attributes on the internet router. For each demo, we are going to try to pin the traffic in specific directions. But the very first thing we're going to do is set up uRPF and at the same time take SRX out and show why SRX will not really work with this scenario. So XR1 is the first router. So again, this is on a per interface based, on a per interface basis. So these are the Ingress Interfaces where this property must be configured. So on XR1, let's go ahead and find out what that interface is. So in this case, that happens to be gig 0000. So interface gig 0000. And the command here is IPv4 verify unicast source reachable via. And now there are two versions available, any and RX. Any happens to be the loose mode uRPF check. So any. And then again, you can use the default route if you want. Other than that, this would be the minimal needed for us because in this lab, we have all of the routes explicitly being advertised and programmed in our fib. We're going to do the same thing for IPv6, verify unicast. And commit this config. So now we have uRPF check on our edge interface. We're going to do the same thing on R2. And this time the interface happens to be G2, so interface G2. Now on iOS routers, there is a special option available where you can log all of the dropped packets, whereas the XR router shows you the counters. As far as I know, there are no uRPF drop counters that are available with the XE. But what you can do is you can log the packets with the use of an access list. So let's go ahead and see what access list we already have configured here. So do show run section access list. And if you can see, there are two access lists here. There is an IPv4 access list. And that all that's doing is it's denying IP any, but it's logging the packets. And we are doing something similar with this v6 access list. The idea behind this is when we configure the uRPF check and a particular packet fails the uRPF check, which in our case, once we introduce the bad guy address for source-based RTBH from the trigger router, it is going to fail the RPF check. What we can then do is any failed packets can then be subjected to an access list. And if the access list allows them, then they're allowed. If the access list doesn't allow them, then they are they remain dropped. But instead of just permitting them or doing anything else, what we are using the access list for is to actually log the packet. So once the packet fails the RPF check, it would be sent to this access list. It would be denied by this line, and we would be able to log the packet. So how to apply this on the interface? IP verify unicast. Don't use the reverse path. That's the deprecated command for this. The source-based command is the one we want to use. Reachable via any. So this is the same command as XR. But as you can see, it allows us to put an access list at the end of it. And I guess in this case, it's only taking access lists that are numbered. So I know for IPv6 it doesn't, but I'll create this access list in a second. So access list 100. And then IPv6 verify unicast source, reachable via any. And now I can actually use the access list that I've defined up here, which is ACL SRTBH v6. Finally, define that access list 100. So access list 100 deny IP any log. And that's all we need to do on here. So both of these routers, the XC and the XR, they've been configured for uRPF checks, and they can start doing source-based RTBH. For the good guy, and by the way, this here should say source, not destination. So I'm reusing some of my material, and that's why this says source, but this should really say destination. Okay, so now on the SRX. The SRX can do uRPF checks. So let's look at the interfaces on the SRX. And I believe the interface here is G001. So show interface G001.0. And as you can see, on at least family INET, I've tried to configure RPF check in loose mode, but what that particular command does not do is it does not take the discard route into consideration. To take the discard route into consideration, at least the platforms that support it, there is a special option available under forwarding option. So if you go to set forwarding options, on a platform, on a Junos platform that supports the discard route drop, there would be a knob called RPF-loose mode-discard. And as you can see, that knob is not available here, so I cannot really do that. So what we are going to do in this case is we're just going to take SRX3 out of the picture. And we're going to do this, we're already doing this on INET 7. So let's look at the routes on INET 7. Show BGP IPv4 unicast. And as you can see, the SRX path has a lower weight, or it has the default weight, while the XC and the XR routes have a higher weight. The reason I'm using weight is it only felt appropriate. We are trying to exclude a Junos device, so why not use something that is iOS proprietary? No, I only half joke here. So the reason to use this is because it lets me configure the weight on a single line. So instead of having a route map, I can just configure it on a single line. But one more thing that we would have to do, because we are using ICMP traffic and we sort of want to see each of the routers being used, we are also going to actually increase and decrease the weights of XR and XC so we can point traffic in certain different directions. But we will do that later. Let's take a look again at our scenarios. So the first one is the next hop attribute-based RTBH. Now, if you remember in this one, all we have to do on RR6, so RR6 may already be primed for it. There are some route maps available here. Show run section route map on RR6. So this is the v4 RTBH route map. We match on a tag, and then we set a next hop that is supposed to be discarded, or supposed to result in a discard on our edge routers. And we're going to bump up the local preference. We are going to change the origin to IGP so it looks pretty. And we are also setting the community of no export so it doesn't leak out. Let's only talk about v4 for this moment, and let's go ahead and look at the BGP of this. Do show run section IPv4. Too many D's. And in this, I have a redistribute static command that goes through that particular route map that we discussed. So any static routes that are now matching tag 666 will go through the route map, and their attributes would be changed, including the next hop to what you see on your screen. Do we have any routes right now? We do not. So let's go ahead, start sending some traffic. But before we do that, I also want to make sure that I am focusing on a single router and not both routers at the same time, because again, this is ICMP traffic. There are no ports. So the traffic would be pinned based on source and destination, and I sort of need to see which router is it going through first. So in order to make that explicit, let's make XR1. Let's make XR1 our preferred router first. So right now, XR1 is going to be preferred, and the way I'll do it is I'll just bump the weight up to 2000, clear the routes out, and then I know for sure that everything is going through XR on INET 7. So router BGP 7, router BGP 7, address family IPv4 Unicast. And then I'm going to pick, this is the address for XR1, and I'm going to bump that weight up to 2000, do clear BGP IPv4 Unicast star soft in, do show BGP IPv4 Unicast. And now if you look at it, 8888 is explicitly going through XR1, and now we can just focus on XR1 for the meanwhile and focus on XR or the XE router after we're done with this. So on RR6, back to RR6, what we are going to now do, actually let's start sending some pings from here. So we'll say ping 8.8.8.8, and remember this is the bad guy address. Source loopback 0, let's go with a high repeat count here. And I'm going to copy this because I'm also going to send these pings from the good guy. And the idea is the bad guy should be blocked while the good guy should still be operational. The address that the bad guy is using is 201, 201, 201, 201. So that's the route we have to block. And simply what we're going to do is IP route 201, 201, 201, 201. It's going to be a /32 route, so we're only blocking that particular source. We'll point it to null 0, but the most important part to send it through the route map is to tag it with 666. Once it's tagged here, you'd see an immediate effect on bad guy 201. We are now dropping its traffic. What about the good guy? Good guy is still operational, so we seem to have succeeded in what we have done. But because there is a null 0 route involved here, we have to absolutely make sure that it is RPF that is doing this, not the reverse path traffic or the return traffic from CEA that is being dropped. So on RR6, let's look at our BGP table. Do show BGP IPv4 Unicast. Here is the route that I'm introducing, and the next hop is being massaged to that 192.0.2.1 address. XR1 is really the only router we are concerned with right now, so do show BGP IPv4 Unicast. There is that route. It is the preferred route because of our local preference. And finally, we have to check the CEF of it. So do show CEF IPv4 201, 201, 201, 201. And it is a null 0 adjacency. So it is a discard route right now. To see the actual drops in action, so we'll say do show CEF drops, I believe is the command on here. So do show CEF drops. And we can see the RPF drops have, there are a significant amount of RPF drops here. They should be increasing, so 118 to 121 to 122. So as each packet is being dropped, those counts are going up. On R2, we haven't triggered any logs, so that means there is no RPF drops, at least on R2 for right now, and that's simply because we are not sending any traffic via R2. So that's it for XR1 and IPv4. Now we have to see the same thing in action on R2, which is the XE router. So what we will do now is we will bump the XR2 weight to 3000. So it's just increasing weights one after another. Again, we're going to clear the routes. Give it a second. And now let's look at the IPv4 Unicast. And now we are sending the traffic through the XE router. So let's go ahead and look on the XE router. And there is our access list, catching the packets and logging them as each and every one of them is being dropped. So for IPv4, that's as far, and IPv4 with the next top attribute, that is as far as we are going to go. Let's talk about IPv6. Remember again that this particular scenario was using 6PE. And one of the problems with 6PE that we discussed last time was even if I put a route map and massage the next hop, as that NLRI is carried over 6PE, so carried over the v4 adjacency, the next hop is massaged back to the IPv4 compatible IPv6 address. So for that, we had created a tunnel here, but that tunnel really is not working right now because the next hop is being unchanged on RR6, so that next hop is still the IPv6 compatible IPv4 address of R4, and even if I do this, it's basically just cosmetic. So we're not going to do the next hop attribute change in our particular case, because with 6PE that is not the best idea. Instead, when we go to communities, which is next, we'll display the communities for both the situations, IPv6 and IPv4. So for IPv4 and next hop attribute manipulation, this is all there is to it. Next is the community-based RTBH. So remember, in community-based RTBH, the trigger router will not change the next hop. Trigger router will just attach the RTBH community, which should be understood within the SP. And when the ASPRs or the edge routers receive that community, so suppose in our case it is 1:666, all of the routes that need to be subjected to RTBH should be tagged with this community. And when this community is finally advertised to the edge routers should have a local policy configured on them to take a look at this community, and any routes tagged with this community would then be pointed to the discard interface. So those route maps and route policies have already been set up on XR1 and R2. So we'll go ahead and display that. So on XR1, let's look at the BGP, show run router BGP. And if you can see on my neighbor 6666, which is RR6, I have two policies, one for IPv6, one for IPv4. So show run route policy. And let's look at the v4 policy first. And in the v4 policy, there is a restriction. So any route, as long as the prefix happens to be between 24 and 32, so no shorter than 24 and as long as 22, but the community must match 1:666. Then I'm just setting the next hop to discard. Elsewise, I'm just letting the route pass through, attributes unmolested, unchanged. And the same thing for v6, and the only difference is the prefix length now is allowed between 64 and 128 because of the longer address. Community match is still the same. The then action is still the same. The else action is still the same. So really all we need to do, XR1 is essentially set up. All we need to do is change the attributes on INET 7. So let's start the attack from here. Actually on here, let me go ahead and do a no locking console just for right now so I can display the route map. So do show run section R BGP. And I have a route map for 6666 in address family IPv4. I have something similar in IPv6. Let's look at these route maps. Do show run section route map. And the map is a little bit more convoluted here. Not everything is visible immediately, but for IPv4, I'm matching a prefix list, I'm matching a community list, and then I'm setting the next hop to 192.0.2.1. So essentially, XE routers do not have a programmatic discard option available, so you essentially are still manipulating the next hop attribute, but you're doing it internally. You're not depending on the NLRI to already have that next hop attribute. So let's take a look at the prefix list, show run, and we are doing the same thing for IPv6. We are matching a community list, we are matching a prefix list, and we are setting a next hop that essentially points to discard. So do show run include prefix list. And the prefix list for IPv4, it's doing the same thing that the route policy was doing on the XR router. It is permitting any route as long as the prefix happens to be greater than 24. And the less than 32 is implicit in this particular statement. We're doing the same thing for IPv6. Any route as long as the prefix is greater than 64 and implicitly less than 128. The other thing is the community list. The community list basically just matches 1:666. So it is the same thing that we were doing via route policy on XR1. I would show you SRX3, but you could just go to the destination-based RTBH demo and it's the exact same thing. Since our traffic is already pointed to, so we had raised this to 3000 right here. So currently our traffic is being passed to R2, so we're just going to use that for, actually no. So that was for IPv4 traffic. So yes, it is for IPv4 traffic, so the v4 demonstration we'll do for R2 first, and we'll reverse the orders this time around. So on RR6, we need to change the route map. Do show run section route map. And specifically, we have to change the route map for v4. So we'll go into this statement. We'll take the next hop attribute manipulation out right here. And we'll set an additional community. Set community 1:666. Exit, do show run section route map. And now you can see there is no next hop attribute manipulation, but we are setting that additional community. Once we do that, let's clear the route out. Do clear BGP IPv4 Unicast R soft out. Do show BGP IPv4 Unicast. And what we need to see is 201.201.201.201 is not being changed yet. And I believe I may just have to redistribute the route again. Nope, I don't. So it has taken care of itself. So the next hop now is 0000. That just says locally originated, but the communities are not visible here. So let's take a look at the community. But 1666 is now being imposed on that route. That means on R2, the idea should still be the same. So do show BGP IPv4 Unicast. And 201.201.201.201 is still being set to 192.0.2.1, but the difference is now it's being set locally. The traffic is still being dropped if you look on bad guy. And if I say logging console 7, I should actually still see those packets being logged by the access list. So now it's already happening here. Time to demo this on XR1. And to do that, we'll basically just lower this weight back to 1000. So remember, the weight for XR is already 2000. We had increased the weight for XC to 3000. We'll lower it back to 1000. We'll clear the route in. We'll wait for a second and we'll verify. And in this verification, now the traffic is going through XR. So what we should see on XR is that drop count should start again. So it's 149, 150, 151, 152. So essentially we are dropping the traffic now based on communities. So the last demo here is for IPv6 and the same thing. So similar effect on IPv6. So before we do that, let's take a look at the current situation of the IPv6 routes. Do show BGP IPv6 Unicast. And right now we have done, oh, this is RR6. So INET 7 is where we want to see this in action. So do show BGP IPv6 Unicast. And as you can see, for 2001:8 or :8::8, we are now load balancing across XR and the XC with the weight. So, and SRX is essentially out, but I want to concentrate on XR1 first. So I'll go into router BGP 7, address family IPv6 Unicast, and I'll take the neighbor statement for XR1 and change the weight to 2000. Clear the route. Do clear BGP IPv6 Unicast R soft in. Wait for a second. Do show BGP IPv6 Unicast. And now the IPv6 traffic is being sent explicitly through XR1. We can begin with our experiment. So let's stop these IPv4 pings on good guy and bad guy. And instead we are going to generate some IPv6 pings. So ping 2001:8:8, source loopback 0, and with a high repeat count. Just keep in mind the address, which is important here. So 2001:201:200:201. Same thing on good guy. Ping 2001:8:8, source loopback 0, high repeat count. And both of these are now able to send the pings because we really haven't put the RTBH in action yet. We can do that. So on R6, let's take a look at the route map for IPv6. Do show run section route map. And that route map is already primed for communities, to use communities from last time. So it matches stack 666, bumps up the local preference, changes the origin, but sets the community to 1:666 plus no export. So both of those things are happening. What about under BGP? Under BGP, we are redistributing any static routes and passing them through that route map. So essentially, if the static route is tagged with that community, the same exact thing that we were doing for v4, it is going to be now tagged, or it is tagged with 666, then it's going to be tagged with the community. The only thing left to do is introduce the route. So let's focus on the bad guy here for a second, and let's introduce the route. IPv6 route 2001:8, or actually it's 201:201/128, and then I'm going to point it to null 0 locally, but tag it with 666. And immediately I can see the traffic being dropped. What about the good guy? Good guy is still able to send the traffic. The bad guy traffic is now being dropped. So there's a good chance that we're using RPF checks to do this. So do show BGP IPv6 Unicast is what I'm interested in. It is a locally originated route with a locally originated next hop. But what about the detail of it? Because I want to see those communities being attached to the route. So here are the communities, 1666, and no export. So next thing we need to go to XR1, do show BGP IPv6 Unicast. I have this particular route, and although it does not really show a next hop, it does show this capital N here, which means the next hop is discard. So it doesn't show the next hop explicitly because remember, in the route policy, for this v6 route policy, we're not setting an explicit next hop. So we're not doing the recursive next hop. We are just literally setting the next hop to discard, and that's why it shows up as this. Let's take a look at the detail of this really quickly. And we can see the next hop is discarded. So the only thing that needs to be done here is look at the CEF, and if you're dropping on the RPF check, so do show CEF IPv6 drops, and there are your RPF drops, 52, 54, 55, and so on and so forth. So we are definitely dropping packets that are failing RPF checks. Well, the very last thing here is now pass that traffic through R2 and see that logging access list in action. And for that, all I need to do is I need to change the neighbor statement for XE, which happens to be this number 2 router here, and bump up the weight to 3000. Clear the routes, wait for a second, verify BGP again. And now I am sending the traffic through the XE router, and I should see some logging happening in here. And there it is. There is your logging. We are dropping traffic that is failing the RPF check from bad guy 201 to our victim, which is 88. Well, no longer the victim, right? Because we have now protected it, and the good guy keeps working. So this essentially shows the advantage that source-based RTBH has over destination-based RTBH. That happens to be all for this time, but in our next video, we will introduce the topic of BGP flow specification or flow spec, which is a vastly superior way of mitigating DOS attacks. Till then, I hope you've enjoyed this video and are looking forward to the next one. Thanks.